This PowerPoint will describe the biochemistry behind the coagulation process. Meg Sell, a 27-year-old Caucasian woman, presents with the chief complaint of weakness. Earlier in the day, she vomited blood. Her physical examination revealed scattered ecchymoses. The physical exam and laboratory data revealed jaundice based on an elevated serum bilirubin and yellowed eyes. This data revealed decreased hematocrit, hemoglobin, consistent with anemia. Blood smears suggested a microangiopathic process based on the presence of anisocytosis, polycytosis, and fragmented red blood cells. Coagulation studies showed that platelet levels are decreased. The PT, PTT, fibrinogen, and D-dimers are all normal, ruling out CIC. She was diagnosed with thrombotic thrombocytopenic purpura. Over time, the endothelial cells that line the blood vessels become damaged, allowing the blood to leak out to the tissues. This is seen in part 2. Platelets recognize damaged blood vessels by the presence of collagen that is exposed when the endothelial cells are absent. The binding of the platelets to the collagen activates the platelets, leading to a flattening of the platelet cell and the secretion of their contents, within their granules. The activated platelets recruit additional platelets to the damaged area. The platelets will also recruit clotting factors to the platelet surface, thereby activating the coagulation cascade, leading to the activation of thrombin. The active thrombin cleaves fibrinogen into fibrin, which is deposited on the top of the platelet plug. This forms a soft clot. The thrombin cascade then activates factor 13, which cross-links the fibrin to form a hard clot. Once the hard clot is formed, the coagulation cascade is shut off. The von Willebrand factor is one of the first molecules that recognizes the presence of damaged blood vessels due to the exposure of collagen. When secreted, the von Willebrand factor has an initial molecular weight of 20 megadaltons, or 20 million daltons. The von Willebrand factor is then cleaved by the protease atom TS13 to multimers that range in molecular weights between 20 megadaltons and 500 kilodaltons. If this is not done, then high molecular weight von Willebrand factor will induce aggregation of the platelets to form thrombi, and thereby removing the platelets from the circulation system so that they can't participate in the coagulation process. Platelets normally circulate in the serum until they encounter damaged blood vessels, as indicated by the exposure of collagen and the presence of von Willebrand factor. Glycoprotein 1b, which is abbreviated GP1b, binds to von Willebrand factor, and glycoprotein 1a, abbreviated GP1a, binds to collagen. Glycoprotein 2b3a binds to von Willebrand factor and to fibrinogen. All both GP1a and GP2b3a belong to the integrin family. Now, the binding of the platelets to the von Willebrand factor activates these platelets. This activation includes the secretion of the alpha and beta granules, activation of the phospholipase C cyclooxygenase pathways, and the rearrangement of the actin cytoskeleton. The change in the cytoskeleton causes the platelets to change from a more elliptical shape to a flat disc-like shape, as seen from the transition between figure A and figure B. The content of the granules that are being secreted, plus the product of the cyclooxygenase pathway, which is thromboxane A2, causes vasoconstriction and the recruitment of coagulation factors and the recruitment of additional platelets. The new platelets are activated so that even more platelets are recruited. This occurs until the plug of platelets has filled in the damaged area within the blood vessel. The secretion of the alpha granules releases the following proteins into the blood supply or on the platelet surface: platelet-derived growth factor, beta thromboglobulin, fibrinogen, factor 5, factor 8, and von Willebrand factor. The von Willebrand factor and fibrinogen help recruit additional platelets to the site of injury by forming bridging contacts between the two platelets. The fibrinogen also serves as a substrate for coagulation cascade. Factors 5 and 8 play a crucial role in accelerating the rate of the coagulation of the clotting cascade. The dense granules secrete calcium, ADP, ATP, and serotonin into the extracellular space, which signals the site of injury. The calcium is especially important as it aids the binding of a number of coagulation factors to the platelet surface, thus localizing the coagulation cascade to the site of injury. The active platelets increase the activity of phospholipase C, resulting in the eventual release of arachidonic acid. This metabolite is converted to thromboxane A2 by the sulfooxygenase pathway, and thromboxane A2 further activates platelets and also causes vasoconstriction. This figure shows a clotting cascade with the factors that are associated with the platelet surface shown in yellow. Clotting factors 2, 7, 9, 10, and 11 are serine proteases. That is, these factors cleave their peptide targets into two parts, and that these factors utilize an aspartic acid, histidine, and serine catalytic triad within the active site. This cascade consists of a series of steps in which the protease in the cascade will cleave its target, thereby activating the next protease in the cascade. This occurs until factor 2, or thrombin, is activated. The intrinsic arm of the cascade is triggered by exposure to collagen, whereas the extrinsic arm of the cascade is triggered by the presence of tissue factor. The cascade proceeds until factor 2, or thrombin, is activated. And once activated, the serine protease thrombin cleaves fibrinogen to make fibrin, which immediately precipitates, polymerizes, and deposits on the surface of the platelets, which is where thrombin is located. Thrombin will also cleave factor 11, another serine protease in the intrinsic pathway. Thrombin will also cleave factor 5 and factor 8, both of which amplify the clotting cascade by bringing the enzyme and the substrates close together. Thrombin also activates factor 13 to initiate fibrin cross-linking, and protein C, which aids in terminating the signal of the clotting cascade. And remember that protein C requires calcium for binding to the platelet surface. This figure shows that the clotting factors 2 and 7, 9 and 10, 7 and 10, and 10 and 2 must associate for the propagation of the coagulation signal. Factors 5 and 8 are shown in blue and become active following a peptide cleavage, which is catalyzed by the enzyme thrombin. Once activated, factor 8 and greatly accelerates the signal cascade by bringing factors 9 and 10 together. Activated factor 5 accelerates the signal cascade by bringing factors 10 and 2 together. Now, all these associations are occurring on the platelet surface. This requires these factors, specifically factors 2, 7, 9, and 10, to have gamma-carboxylated glutamic acids, which allows these factors to bind to the surface of the activated platelets in a calcium-dependent manner. Remember that the calcium is secreted when platelets are activated. Now, the presence of gamma-carboxylated glutamic acids requires a post-translational change in the protein when it's being synthesized. In order for clotting factors 2, 7, 9, and 10 to associate with the surface of activated platelets, many of the glutamic acids, which are highlighted by the orange circle, must be converted into gamma-carboxylated glutamic acid, which is highlighted by the red circle. This reaction is catalyzed by vitamin K-dependent carboxylase, an enzyme that utilizes reduced vitamin K, that is the hydroquinone form, as a substrate, and produces oxidized vitamin K, the epoxide form, as a product. This enzyme also utilizes molecular oxygen and carbon dioxide as substrates. The oxidized form of vitamin K can be reduced back to the original hydroquinone form in 2 steps. The first reaction being catalyzed by vitamin K epoxide reductase, and the second reaction being catalyzed by vitamin K reductase, thus regenerating the original hydroquinone form of the enzyme. Both steps, reduction steps, usually use dithiols such as lipoic acid, as a source of reducing equivalents. Some vitamin K reductases can also use NADPH as a source of reducing equivalents. And note that all of these reactions are taking place in the liver. The small molecule warfarin, also called coumadin, inhibits coagulation. Notice that the structure of warfarin on the right resembles the structure of vitamin K, which is on the left. Warfarin binds to the active site of vitamin K epoxide reductase, thereby inhibiting this enzyme. Because warfarin blocks this step, vitamin K cannot be reconverted to its hydroxyquinone form. This in turn will prevent many of the coagulation factors from binding to the surface of activated platelets. Now this figure is to remind me to tell you that the ultimate goal of the coagulation cascade is to activate thrombin to cleave fibrinogen, producing the insoluble fibrin that deposits on the platelet plug. Fibrinogen is made by both hepatocytes and platelets. Extracellular fibrinogen is a hexameric protein made by two heterotrimeric halves, each of which is made from an alpha, beta, and gamma chains. The three chains are held together by a triple helix. Upon secretion, fibrinogen contains a highly negative charged N-terminal region on the alpha and beta chains, which is shown in red in this particular figure. The negative charge prevents the fibrinogen from its aggregating. However, when activated, thrombin cleaves the negatively charged N-terminal peptides from the alpha and beta chains. This leads to the polymerization of fibrin to form a fairly regular repeating mesh, as shown in the figure. The fibrin is deposited on the platelet plug to form a soft clot. The clot at this point in time can be solubilized by denaturants such as urea. The next step in the coagulation cascade is to cross-link the fibrin. The cross-link is accomplished by forming an amide bond between a lysine from one fibrin molecule and the glutamine from a second neighboring fibrin. The amide bond in this figure is shown by a red circle. This reaction is catalyzed by factor 13, which is a transglutaminase. And note that the reaction gives off ammonia as a byproduct. The figure on the right shows the organization of the soft clot, which is very systematic, and the organization of the hard clot that is formed following the cross-linking reaction. And in the hard clot, the cross-links are shown as green lines. And note that the lines are between the various fibrin monomers or fibrin monomer units with each other. Now, this particular cross-linking reaction makes the clot very resistant to mechanical and chemical stress, and that this clot, once cross-linked, will not be able to be dissolved in urea. And in fact, patients with clots that can be dissolved in urea are likely to have a defect in factor 13. The last step of repair is to turn off the coagulation cascade. And the initial signal for turning off the coagulation cascade is made by thrombin. Thrombin, in the presence of thrombomodulin, will cleave off the peptide from protein C, forming active protein C. And active protein C, in the presence of calcium, will associate with protein S. And together, this protein FC complex will photolytically degrade factors 5 and factor 8. Thus slowing down the coagulation cascade. The activity of thrombin is also regulated by a number of small molecules that are present in the bloodstream. This would include serine protease inhibitors such as antithrombin 3, and thus the thrombin activity will be inhibited very shortly after it's activated. The last step in turning off coagulation involves turning on fibrinolysis. This switch is in part mediated by activated protein C, which stimulates the release of tissue plasminogen activator, which is abbreviated TPA in this figure, and it also inhibits plasminogen activator inhibitor, which is abbreviated PAI1. TPA is a serine protease that cleaves a peptide off of plasminogen to form plasmid. The conversion of plasminogen to plasmid is also catalyzed by urokinase, which is abbreviated UPA in this figure. Plasmid is a serine protease that degrades fibrin to produce fibrin degradation products such as D-dimer. Therefore, high levels of D-dimer indicate high levels of fibrinolysis. Note that in this figure, the catalytic activity of plasmin is inhibited by alpha-2 antiplasmin. Now, this figure shows three major coagulation disorders that result in a decrease in platelet count. The first two of these disorders are caused by autoimmune reactions. In the case of idiopathic thrombocytopenic purpura, the antibodies are directed against one of the platelet glycoproteins, such as glycoprotein 1b or glycoprotein 2b3a. ITP is characterized by petechial hemorrhages. In the case of thrombotic thrombocytopenic purpura, the antibody is directed against ADAMTS13, leading to increased high molecular weight von Willebrand factor and microthrombi. The microthrombi causes microangiopathic hemolysis and blood loss, both of which leads to anemia. Now, disseminated intravascular coagulation, or DIC, leads to the formation and destruction of thrombi, leading to a reduction of platelets, fibrinogen, and clotting factors. DIC also results in an increase in D-dimers, the product of fibrin degradation, and an increase in PT and PTT times because of the reduction of the coagulation factors. Now, to conclude, Mexel, a 27-year-old Caucasian woman, presents with the chief complaint of weakness. Earlier in the day, she vomited blood. Physical examination and laboratory data revealed scattered ecchymoses, jaundice, and anemia. Blood smears show the presence of anacytosis, polykystosis, and fragmented red blood cells. Coagulation studies showed that the platelet levels are decreased. The PT, PTT, fibrinogen, and D-dimers are all normal, ruling out DIC. She was diagnosed with thrombotic thrombocytopenic purpura and associated with microangiopathic hemolysis. That's it for this talk.